Hi. So, in our last discussion, we said that although sexual evolution ends up explaining a large number of things in biology, there are certain patterns which even sexual selection or sexual evolution of sex cannot explain. And I said one of those things is the phenomena of honeybees. Now, all of you would have seen honeybees or wasps or ants, and as you know, they make these very nice intricate nests. So, I am here showing you the hive of a honeybee, the nest of the harvester ants, which you can find quite a bit in India. But the reason these organisms are important or enigmatic to biology is not because they can make such intricate nests. Many other organisms can do the same. But the reason these are very important is because they exhibit a certain phenomena known as eusociality. Now, what exactly is eusociality? So, there are 4 major characters, and in order for an organism to be called as eusocial, all 4 characters need to be present together. So, the first character is that the adults must be living in groups. Of course, many other organisms also do that. For example, zebras or wildebeests, they also live in groups. But the next character, which is very important, is that there has to be cooperative child care. So, individuals should take care even for those children which are not always their own, and this is perhaps the most important one. There has to be a reproductive division of labor, which means that not all individuals will get to reproduce, and finally, there has to be an overlap of generations at the same nest or the same nesting place. Now, individually many organisms will show one character or the other, which is why in order for something to be called as eusocial, all 4 characters need to be present together. And as you know, prime examples are honeybees, wasps, termites, ants, naked mole rats, and so on. Now, there are 2 major things in these eusocial animals which actually lead to a lot of explanation that are needed from evolutionary biologists. The first thing is that, as we said, that in many of these organisms only a small fraction of the total colony breeds. So, for example, here I am showing you the honeybee queen, the one which has a green marking on its body. You can see that it is so much larger than all the other workers, and all these workers are sterile. An even bigger size disparity is in terms of the queens of the leafcutter ants Atacolombica. So, here you see the queen, and these small things over here, these are the workers. Now, the interesting thing over here, as I said, is that the workers do not reproduce, and therefore, their fitness is 0. That entire colony, the hive, whatever, actually represents only the kids of the queens, and they have all the fitness. All the millions of workers have 0 fitness. The other very interesting thing in the context of eusocial animals often is that they will often end up sacrificing themselves for the sake of the colony or the hive. So, for example, here is a honeybee, and you know that honeybees, when they sting, it really hurts, and more importantly, when they sting and they go away, the sting actually remains in the body of the organism, particularly if it is a vertebrate, and this is because the skin has barbs in it. And the problem is that when the sting is left in the body, the sting actually continues to pump venom into the body of the victim. But on the other hand, when the sting is left inside the body of the victim, as you can see over here, this white part that you are seeing, that white part is actually the inner organs of the bee. So, the sting actually, when it is detached from the body, it takes much of the organs of the worker's body with it, and therefore, the honeybee which stings actually dies within 15 to 20 minutes. So, it is a suicide mission on which it ends up stinging an intruder. Similarly, if you look at an ant colony, again the soldier ants much of the time they actually just end up dying, in the process of defending their colony. And both these aspects, obviously these are leading to zero fitness for the worker or the soldier. And this is what has been a massive headache for biologists even since the time of Darwin, that why is it that the workers or the soldiers, they give up their fitness for the sake of the mother or for the sake of their colony mates. Now, although here I am talking about eusocial organisms, if you look at it closely, even in non-eusocial organisms, there are many which behave in such a way that it ends up reducing their fitness while ending up benefiting another organism. Now, in biology, this phenomena whereby the action of an organism ends up reducing the fitness of the actor, but ends up enhancing the fitness of somebody else, this is what is known as an altruistic act, and the phenomena is known as altruism. Now, this is a bit different from how we use the word altruism or an altruistic act in regular English usage. So, in let us say in the human society, suppose somebody comes and asks me for a few rupees and I give that person a few rupees. Then the reason that I am giving it probably has some kind of a moral angle to it, and under many situations I actually incur no major cost, no major disadvantage by giving those few rupees, right. So, in the context of regular social usage, an altruistic act does not necessarily have to be an expensive thing for the actor. Okay. There basically it is defined along moral terms, whereas in the context of biology, an act is altruistic if and only if it reduces the fitness of the person or the organism who is committing the act, and at the same time it is enhancing the fitness of another organism towards whom the act is being done. So, this is a very crucial difference that one has to keep in mind. Now, the whole problem over here is that natural selection is always trying to enhance the fitness of the individual. Anything that reduces the fitness of the individual under normal situation should not be selected for. But if that be the case, how can these kinds of things that I am telling you in the honeybees and the ants, where the actors are giving up on their fitness, how can such a thing be selected for, or how can such a thing even exist in the presence of natural selection? So, that is the crucial question over here, and of course, this is a question that did not escape Darwin's notice, and he himself puzzled quite a bit about it, and there have been many other people who have thought about it later on. So, I will give you a quick answer. Okay, the main story I will give you straight away. So, the quick answer to this conundrum is that if you have an action which reduces the lifetime direct fitness of an individual. What do I mean by direct fitness? I mean the number of individuals, the offspring that this particular organism produces, that is the direct fitness. Now, if there is an action which ends up reducing the direct fitness of the individual, but enhances its lifetime inclusive fitness. Now, what do I mean by lifetime inclusive fitness? So, the inclusive fitness is the direct fitness of an organism plus the fitness of the relatives of that organism. So, that is this sum, my fitness plus my relatives fitness, this sum is what is known as inclusive fitness, and we need to look at the lifetime inclusive fitness, which means over the entire lifetime of both me and my relatives. So, if there is something which reduces the direct fitness, but increases the inclusive fitness, then under certain circumstances, this is very critical over here, under certain circumstances the trait can actually be favored by selection. And this phenomena wherein it is the inclusive fitness which is being selected for rather than the direct fitness. This phenomena is what is known as kin selection. Now, of course, much of today's discussion is trying to figure out what this under certain circumstances mean, okay, but we will get to there over the next few minutes. Now, as I said, this problem of eusocial organisms committing suicide and essentially doing things which is doing nothing for their fitness, this problem was spotted by Darwin himself. He thought a lot about it. He came up with this kin selection answer in some ways. Echoes of this you can find in the work of Ronald Fisher. 1955 J.B.S. Halden very famously gave some back of the envelope calculations for this. But the person who actually formalized this relationship and kind of made it come to the consciousness of most evolutionary biologists is the British evolutionary biologist William D. Hamilton, right. So, in order to understand what exactly Hamilton said, we have to understand the concept of inclusive fitness. And in order to understand the concept of inclusive fitness, we first need to understand what exactly is meant by a relative. Who is a relative of an organism? But before we go there, we need to understand one concept, okay, just one. And that concept is the concept of identity by descent. Why do we need this? It will become clear as soon as I tell you what it is. So, suppose you have a diploid organism and let us assume that there are two identical alleles at a given locus in a given individual. Okay. So, when I say identical, I mean that let us say both of them are capital A, capital A. Okay. And so, the genotype of the individual is AA, the genotype the individual is homozygous for capital A allele. Now, this individual could have gotten this capital A allele in two different ways. One way is when these two capital A alleles are copies of some ancestral allele. Okay. The single ancestral allele has led to both these alleles in this focal individual. When you have a scenario like this, then you say that these two alleles are identical by descent, right. So, by definition that means that they are copies of the same ancestral allele. What is the other way in which the same thing can happen? The other ways the same thing can happen is that sure the organism has two capital A alleles, but the origins of these alleles are different. They are not copies of the same ancestral allele. And if you have a situation like this, that is what is known as identical by state. Now, why do we need this concept? What is the meaning of this concept? So, suppose you have two individuals. Okay. So, let us say this is one individual and let us say this is another individual, and let us say inside this individual you have this allele and you have this allele. Now, if you can show that both these alleles they are actually copies of an ancestral allele, that is they are identical by descent, then you can say that these two individuals are related to each other, right. And the greater is the probability that these two alleles are identical by descent, the greater is the or the closer is their relatedness to each other. That thing will become clear in the very next slide, but essentially if these two are copies of the same ancestral allele, you can say that these two individuals then are related to each other. On the other hand, let us say this allele has come from one source, this allele has come from a completely different source, then even if they are the same allele, you can say that they are probably coming from different sources, which means that they are not related to each other, or the chances of their being related to each other is much lower. So, this concept of identity by descent, it actually allows us to evaluate how closely two organisms are related to each other. How exactly does it do that? Let us figure out. So, in order to do that, you need the second concept, which is known as relatedness. So, relatedness is the probability that two individuals share an allele that is identical by descent, that is it. Okay. Now, it is very easy to express and it is actually not at all complicated, but there are several people who end up getting slightly confused with this one. Okay. That is why I am going to spend a little bit of a time to spell it out in detail what this means and how exactly one can calculate it. Now, let me confess over here, I am one of the people who have always been very confused by calculation of relatedness, which is why I am kind of going out of my way to spell it out in a little bit of detail. If you are one of those people who are very good with probability, then you might think that this is too easy, but trust me, there are many people, a majority of the people are actually like me, they find it difficult to get the calculation, which is why it might be a good idea, even if you understand it nicely, to pay some attention to how to get this done. Now, let us assume an autosomal one locus scenario in a diploid organism, and let us assume that at that locus, okay, I mean you do not have to assume, if it is a diploid organism, then at that locus the individual can have only two alleles, nothing else, right. Now, we will deal with 4 or 5 cases one after the other. So, the first case is what is an individual's relatedness with itself. Now, suppose you have the individual and let us say the individual's alleles are A1 and A2. So, these all that I am showing you over here is that these two alleles are not identical by descent. So, in terms of their actual state, they can be capital A, they can be capital A, small a, whatever the case, but here 1 and 2 is simply showing that they are not IBD. Now, suppose I have picked one allele of these two, right. Let us say just by chance I have picked this A1 allele. Now, what is the probability that I am going to find the A1 allele, a copy of the A1 allele in this individual? And the probability of that obviously is 1, because I know that the individual's genotype is A1, A2. So, whichever allele I pick, A1 or A2, the probability that I will find that allele in the organism itself is 1, is certain, right, which is why an individual's relatedness with itself is always counted as 1. So, now we go to case 2, parent offspring relatedness. So, suppose you have suppose you have a parent, and let us say from that parent we have got an offspring. Okay. What is the relatedness between these two? Now, again let us assume that the parent's genotype is A1, A2. Again, all I am showing is that these two are not identical by descent, that is it. Now, suppose I pick any one allele from the parent, any one, let us say by thing I pick this one. Now, we know that in a diploid organism, a parent is going to pass either this allele to its offspring or it will pass this allele to its offspring, and assuming normal meiosis everything, the probability of passing this allele is 50% and the probability of passing this allele is 50%. Therefore, if I pick up any one allele at random from the parent, the probability that the parent has passed on that allele to the offspring is going to be 50%, right, because I will either pick A1 or I will pick A2, and the probability that whichever I pick is the one that has been inherited to that offspring is 50%. Therefore, parent offspring relatedness is equal to 50%, which is equal to 1 by 2, equal to 0.5. Okay. So, if you just remember this thing, that parent offspring relatedness is 1 by 2, then all the further calculations actually become extremely simple. Let us now look at the third case, where we are talking about relatedness between full sibs. Okay. So, let us assume that this is the male parent, the circle is the female parent, and let us say that they have given birth to 2 kids, one male, one female, and we want to know what is the relatedness between these two, C and D, right. So, let us assume that we have again two alleles over here, and let us say we pick any one of the alleles in random, right. Now, we know that the probability that this kid has gotten this allele from the father is 50%, 1 by 2, right. So, the probability that this allele it has got from its father is 50%. Now, what is the probability that whichever allele I picked over here is the allele that the father has passed to this kid? Remember, both alleles have equal probability of being passed. Therefore, the probability that the father has passed that one to this daughter is again half. So, the probability that this allele is shared between C and D, the two full sibs, is half into half, 1 by 4, right. But this does not complete the calculation. Why? Because remember, there are two alleles at that locus, right. So, it is entirely possible that I could have picked up in the first case an allele which actually this C received from the mother B. So, in other words, I could have got the allele which is received from its mother B with a probability half, and what is the probability that the mother had passed that same allele to D? That probability is again half. So, this is D over here, this is D over here, this is half. So, the product of these two, that is the same allele has been passed from the parent from C via B, or rather from B to both C and D, is equal to half into half, 1 by 4. Therefore, the total probability of finding an allele which is identical by descent in both this and this, the full sibs, is equal to 1 by 4 plus 1 by 4 is equal to 1 by 2. Okay. So, relatedness between full sibs is equal to 1 by 2, right. So, you can see that there is a simple way of doing this, which is that simply figure out the parent offspring relationship, and for each parent offspring transition just put half, because that two alleles and half is the probability of one allele going to that parent or to the other one, and then simply multiply these probabilities. So, this multiplication is going to give you the probability of sharing one allele through this parent between this individual and this individual, and similarly this is going to give you the probability of sharing that allele from the other parent. So, all you have to do for cases like these is to figure out these paths, and for every transition put half, okay, and then take the multiplication along any path and then sum it up for all the paths. So, I will just show you what I mean in one more situation. So, let us assume that we have a situation like this, where D and E are what are known as half sibs. What does that mean? They have one parent which is common. So, in this case the common parent is the mother B, and B has mated with two separate individuals. When she has mated with A, D has been born, and when she has mated with C, E has been born, right. Now, in this case, remember, whatever alleles A has, A cannot pass those alleles to E, right. Similarly, whatever alleles C has, C cannot pass those alleles to D, right, because that is, you can see it from the genetics, right, from the pedigree. Therefore, in this pedigree, A and C do not really matter for calculating the relatedness between D and D. So, here all that we have is D to B and B to E, and D to B is half and B to E is another half. So, the total is equal to 1 by 4 and that is it. Okay. Remember, A cannot contribute to E, D cannot or C cannot contribute to D. That is why there is no second path as we had for the full sieves, and therefore, the relatedness between half sieves is equal to 1 by 4. We will do one more case. This is a little bit of a complicated case, but if you do the path thing, it becomes very, very simple. So, this is the case of first cousins. So, A and B are the ancestors. They had two kids C and D. C married to F, D married to E, D and F and E are from outside the family, and now C and F have a kid G, D and E have a kid H. So, G and H are first cousins. What is the relatedness between G and H? So, again remember, F cannot contribute to H, E cannot contribute to G. So, in some sense all that is gone, you do not really need to think about it. So, what are the paths? So, G to C to A to D to H, this is one path, right? Half, 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 half. This is through the father, correct? You can have one more path which goes from G to C to B, the grandmother, to D to H. So, G to C to B to D to H, again half, half, half and half. So, for this path half, 1/4, 1/8, 1/16, this is 1 by 16, half, 1/4, 1/8, 1/16, 1 by 16. So, the sum of this is equal to 2 by 16, which is equal to 1 by 8, right. So, the relatedness between first cousins is 1 by 8. So, this method that I am showing you, you can use it for pretty much any pedigree that you have. All you have to do is to figure out all the paths which are connecting the two individuals between whom you want to calculate the relatedness, and for each one of the parent offspring pairs, just put it as half, half, half and multiply all of them. For each path you will get one value, sum all those values up, right. So, obviously, the greater the value of the relatedness, the more closely are they related to each other. I mean, an individual is related to itself perfectly, which is, I mean, you can't get anything better than that. Similarly, an individual is related to its clone by a relatedness of 1. Now, given all this backdrop, when exactly is altruism favored by selection? Now, in order to understand this, we have to start with a derivation. So, let us assume that we have a one locus system in which the A1 allele is extremely rare. That means, the number of A1 individuals are so small that they can be neglected. This is an assumption. So, we are assuming that the system is just starting and A1 individuals are very, very small or almost not there. This should not be too hard to assume, because remember, when we were reading about Hardy-Weinberg equilibrium, we saw that when an allele is extremely rare in the population, then most of the copies of those alleles, that allele is actually in the heterozygotes, right. So, similar stuff here. Now, also assume that all the genotypes produce equal number of babies, which means their fitness is equal. Now, let us assume that our focal individual is one who has a genotype A1, A2. Now, since the allele A1 is extremely rare in the population, you can assume that the probability of an A1, A2 individual interacting, okay, this is not mating, interacting with another A1, A2 individual is equal to the relatedness of the two individuals which is equal to R, right. This is an assumption that you have to make. Now, we are going to look at two cases. The first case is where you have no altruism and I am going to call it as NA, right. So, let us assume that we have a focal individual and this focal individual I am going to call it the person as an actor, and let us assume that we have an interacting individual who I am going to call as a recipient. So, this is the first case when there is no altruism. So, there is actually no difference between the focal individual and the interacting individual except in one way. What is that? So, by our very assumption, the probability that the recipient is also an A1 A2 is small r, right. So, we start by assuming that the fitnesses are equal for both. So, the fitnesses of both are equal to W. Now, what will be the number of A1 alleles which are coming out of this interaction? That number is going to be, total number is going to be P N A, Na means no altruism, equal to W by 2. Why W by 2? Because each A1 A2 individual is producing W babies and half of those are going to carry A1 allele. Therefore, P N A equal to W by 2, by 2 is because of the half, plus R into W by 2. Why? Because we know that these two are going to interact with each other with a probability which is going to be equal to R. So, P N A equal to W by 2 plus R W by 2, which simply equals to, you take the W by 2 common outside. So, this equal to W by 2 into 1 plus R. This is my P N A. Now, we introduce altruism. We start exactly the same. You have the focal individual, the actor, the interacting individual, the recipient, and the probability that the recipient is also an A1 A2 is R, right. So, now we have altruism in the mix. What does that mean? That means that the fitness of the actor gets reduced by some amount when it interacts with the recipient, and that reduction we are going to call it C. So, the fitness over here becomes W minus C. Now, what happens to the fitness of the recipient? Remember, in the absence of altruism, the fitness of the recipient is RW, but now what is going to happen is, I am sorry, the fitness of the recipient in the absence of altruism is W. So, the fitness in the presence of altruism is W plus B, right. Now, please appreciate that C and B do not need to be equal to each other. Just because I am paying, let us say 10 units of cost, does not necessarily mean that the recipient is also reaping 10 units of benefit, no. So, which is why C and B do not necessarily need to be the same thing. So, fitness of this is W minus C, fitness of this is W plus B. Now, the number of A1 alleles which are coming out of this interaction, what is that going to be? For the, so this is what I am going to call PA, A is for altruism. So, PA is going to be W minus C by 2, right, because this is the fitness of W, the actor, and half of the alleles that it produces are going to be the A1 allele. Therefore, W minus C by 2 plus R into W plus B by 2, right, because the probability that this interaction happens at all R into W plus B, and then you divide it by 2, because half the alleles that are being produced are going to be A1. So, let us just finish off the derivation here. So, we said that, just we will go back here, PA is equal to W minus C by 2 plus R into W plus B by 2 equal to, take the 2 below, W minus C plus RW plus RB by 2 equal to, we can take W common over here, we take W common 1 plus R plus R B minus C whole by 2 equal to, I can simply write this as W 1 plus R by 2 plus R B minus C by 2, right. This is my P A, and if you remember, my P no altruism is equal to W into 1 plus R by 2. Now, for this thing, for the A1 allele, which is the altruism allele, to increase in the population, P A, which is P altruism, has to be greater than P N A, right. The fitness increase of the A1 allele in the presence of the altruism scenario has to be greater than the no altruism scenario. So, P A has to be greater than P N A. In other words, what is my P A? W into 1 plus R by 2 plus R B minus C by 2 has to be greater than W into 1 plus R by 2, right. So, I have a W into 1 plus R by 2 on both sides, I get rid of it. So, R B minus C by 2 has to be greater than equal to 0, greater than equal to 0, not equal to, or R B minus C has to be greater than 0, or R B has to be greater than C, right. This is the condition that we are deriving. What does that mean? That means that the A1 allele, which in this particular case, as we saw under the condition of altruism is the altruism allele, is going to be favored by selection if the product R B is greater than C, which is also can be stated as genes spread via kin selection if the relatedness R of a recipient to an altruistic actor multiplied by the fitness benefit B received outweighs the fitness cost C to the actor, right. So, the relatedness R of a recipient to an altruistic actor multiplied by the fitness benefit B received outweighs greater than the fitness cost C to the actor. So, this relationship is what is known as Hamilton's rule, which was proposed in a very famous paper, actually two back to back papers by W.D. Hamilton. Now, this sounds great, but why does this explain why honeybees are eusocial, or why does this explain why wasps or anything else is eusocial? So, turns out that honeybees, wasps, ants, all these are what are known as hymenopterans. This is a particular order of the insects, and these insects, they have a very peculiar system of sex determination known as haplodiploidy. What is haplodiploidy? So, in haplodiploidy, the males are haploid and the females are diploid, which means that the female gametes are formed through meiosis, through reduction division. The male gametes are not formed by meiosis, right. Now, in a honeybee society, the females, which means the queens and the workers, they arise when there is a fertilization of the male and the female gamete. However, the male gametes or the males, also known as the drones, they arise parthenogenetically from haploid female gametes. Now, this actually leads to a very peculiar scenario. What is the scenario? So, this is the male, this is the female, this is the queen basically, and these are, let us say, two females who are sisters. So, let us say these are two workers. Now, what is the relatedness between the mother and let us say B or her daughter. So, what I mean by is what is the relatedness between B and say C or B and D. So, we know that parent offspring relationship in a diploid situation is 1 by 2. So, this is 1 by 2. Okay. But what is the relatedness between C and D? Now, let us assume, so if you are talking about C and D, so let us do our path. So, you have a allele, let us say C inherits it from B and then B passes the same allele to D, right. So, what is the probability that C will inherit a particular allele from B? That probability is half. What is the probability that B will pass on the same allele to D? The probability is again half. So, half into half is equal to 1 by 4, no problem. But you also have one more route via A, the father. So, C to A, right. Now, remember this is a female. So, it has got 2 alleles. So, if I pick a allele at random, the probability that it has got that allele from its father is half. Okay. So, the probability that it has got that from its father is half, no issues. But if C has got that allele from the father A, what is the probability that A has passed that allele to D? That probability A to D in this particular case is actually 1. Why? That is because A, the father, is passing its entire genome to the daughter. Therefore, anything that A has given to C is the same thing that A is also going to give to D, right. Therefore, this thing over here is not half, this thing over here is 1, and therefore, this multiplication is going to be half, and therefore, the total relatedness between C and D is actually half plus 1 by 4 is equal to 3 by 4 is equal to 0.75. Here this is equal to 0.5. Okay. Now, note over here I am making a simplifying assumption that C and D have the same father and the same mother. Now, in the context of a honeybee hive, this is fine because there is only one mother for all the workers, but this mother actually can and does mate multiple times. So, theoretically speaking, it is possible that the fathers are of 2 workers are different, in which case this calculation is not going to work, the relatedness is going to be lower. But as long as the fathers are the same, the 2 workers are going to be related to each other by 0.75, which is greater than the relatedness between the mother and her offspring. Now, how does this explain why honeybees are altruistic? So, this explains why honeybees are altruistic because of a very interesting point. What is that point? See, because the relatedness between the mother and the offspring is 0.5, if suppose this particular worker hypothetically were to reproduce, the relatedness between her and her offspring is again going to be 0.5, right. But her relatedness with her sister is actually greater than that. Therefore, she is going to be evolutionarily favored, she is going to pass on a greater fraction of her genes if she ends up helping her daughters, helping her sisters rather than helping her own daughter, or rather than even creating her own daughter. And that is why it is better for us, better in the sense of evolution, better in the sense of having a greater fitness, that this daughter over here, she ends up helping her mother in raising the mother's babies who are her sisters, and if necessary sacrifice herself than produce daughters of her own. Okay. So, this is entirely coming from the fact that you have this very peculiar haplodiploidy kind of a sex determination in the Hymenopterans. Now, this is what explains the altruistic behavior. Now, this Hamilton's rule was actually a massive conceptual leap. It predicted that haplodiploidy, kind of a sex determination, is what will lead to eusociality, and in the 60s and 70s, when people were studying the eusocial organisms, an overwhelming majority of those organisms were actually hymenopterans, the ants, the bees, the wasps, etc., all of which were haplodiploid. And therefore, people thought that yes, this is a mega thing that is explaining so much of biological phenomena. More importantly, this gave a general condition for when there should be cooperation. Okay. Of course, it explains eusociality in hymenopterans, but even if you do not have hymenopterans, let us say you have human beings, this explains why human beings typically end up being more partial or being more favorable to people who are their relatives than people, let us say, who are not related to them, or why they are more partial to people who are closely related to them, their own sons or daughters, etc., rather than, let us say, third cousin or fourth cousin or something else. So, people obviously thought that this is a very big deal until the counter examples started to emerge. So, as I said, during the 60s and the 70s, many of the, or an overwhelming majority of the eusocial animals, they were all hymenopterans which were haplodiploid. But then people started seeing situations where you do not have haplodiploidy, yet you have eusocial animals. So, for example, there are these gall making aphids, these are the only exceptions, but apart from that, no clonally reproducing animal has evolved eusociality. Now, this is very problematic because clonally reproducing animals, as I told you, all clones are related to each other by 1, right, that is the highest form of relatedness that you can have. So, by the logic that we made, those clonally reproducing animals should be a much bigger candidate for evolving eusociality, yet except one species, one group, nobody else had. Then, if haplodiploidy is the primary driver of eusociality, then most hymenopterans should have eusociality. But turns out that hymenopterans are actually a huge group, and in fact, most of them are actually solitary. So, for example, many bees, they are all solitary. It is only the honeybees and a few others which have evolved eusociality. The numbers which have not evolved eusociality in hymenopterans is actually probably larger. And other hugely successful eusocial groups are the termites, and they are diploid, and so are the naked mole rats, which are mammals and diploid. So, and obviously exhibit eusociality. So, turns out that haplodiploidy equal to eusociality, that logic was not really making sense. Now, while this was happening on the empirical front, right from the time when the whole theory was propounded by Hamilton, the theoreticians were actually saying that look, things are probably need to be taken with a pinch of salt. So, if you remember, when we were deriving the whole thing, we saw that the entire thing works only when the altruistic allele has a very low frequency, such that we can completely ignore the A1A1 homozygotes, right. Now, that is okay during the initial stages, but if the altruistic allele is going to be successful, altruism is going to spread in the population, then very soon the frequency of the A1 allele is going to go up, and at that point you cannot really neglect the frequency of the altruistic heterozygote allele, right. I am sorry, altruistic homozygous genotype. Secondly, this derivation, if you saw it, I simply added the costs and the benefits to get hold of the fitness. But in many cases, the cost and the benefits are not going to be additive, they are going to be non-additive. If that happens, one can show that this entire thing can fail. Similarly, the way we did the derivation, we saw that it is only in the context of pairwise interactions. But many interactions in real life are not pairwise interactions, they are 1:many or many:1 or many:many kind of interactions, right. And finally, it is shown that in many cases, our derivation was in the context of one locus. The moment you increase the number of locus from 1 to 2 or anything higher, in many cases the entire thing actually fails. Now, to be fair, these things were not said in the 90s or so. These things people started talking about them 74, 78 and so on and so forth. In spite of that, many people were completely taken over by the elegance of that cute little relationship, until things came to a head in the year 2010. So, in that year, 3 very famous biologists, Martin Nowak, Corina Ternita and E.O. Wilson, they published an analysis paper in Nature called The Evolution of Eusociality. And Martin Nowak is of course a big name. E.O. Wilson is like the father of the subject called sociobiology. His book called Sociobiology launches the study of social organisms in many ways. Okay, I mean, not entirely, but he is one of those people who did an enormous amount of work in making sociobiology a big thing. So, when E.O. Wilson says something, you have to take it a bit seriously. And what E.O. Wilson and others were saying, I am just quoting from that paper: inclusive fitness theory is an alternative accounting method that works in a very limited domain. Even in the limited domain of inclusive fitness theory, Hamilton's rule does not hold in general, and there are no predictions that are specific to inclusive fitness theory, right. These were very bold claims, and essentially the rest of the paper was trying to come up with a slightly different formulation, which does not even need to use inclusive fitness or kin selection to explain the evolution of eusociality. Now, the reaction to this paper was absolute electric. So, there was a massive uproar in the field, and people started writing rebuttals left, right and center. Nature itself 1 year later published a few of those rebuttals, including they published multiple rebuttals. All the rebuttals did not even get into Nature, they did not have space. So, many of those rebuttals got published in other journals, and in particular one of those rebuttals was signed by 103 researchers, and many of those people, they are almost as famous as the authors of the original paper, Nowak and Wilson, right. So, this tells you that there was a serious bit of upheaval in the field, and this paper, the Abbott et al. Paper, argued that Nowak et al.'s arguments are based upon a misunderstanding of evolutionary theory and a misrepresentation of the empirical literature. I mean, this is as strongly worded a criticism as one can make. However, I mean, at the same time, the other papers that came out, they were equally scathing, and basically everybody was saying the same thing: these people have completely lost it. However, Nowak et al. Stuck to their point and stated that it is the other people who have not really understood what they were trying to say. So, the period between 2010 to 2025 has been an extremely fertile period in this context, and it has seen a lot of work on this topic. I mean, when you have something which is like dividing the field into two opposing camps, and both camps are claiming that the other camp is getting it completely wrong, you realize that there is something very fundamental happening. And over these 15 years, people have really tried to figure out what are those fundamental differences because of which the two sides are talking past to each other. So, as I said, they have scientists and philosophers carefully examined both positions and tried to figure out where the debate was coming from. So, for example, in 2014, Birch argued that there are actually two versions of Hamilton's rule, not one, and he called them, like general theory of relativity, special theory of relativity, he called them general Hamilton's rule and special Hamilton's rule. And he showed that much of the debate is actually arising because people are not distinguishing between these two when they are arguing with each other. Similarly, in the same year 2014, there was a nice review paper by Bork where he examined the empirical examples in favor of Hamilton's rule. Now, appreciate one thing, that although Hamilton's rule is very easy to express, figuring out the exact value of B and C is an empirical nightmare. Why? Because B is benefit over the entire lifetime, C is cost over the entire lifetime. So, how are you going to figure out how much cost and how much benefit a particular action of a individual organism is going to lead to? So, in spite of that problem, Bork actually identified 12 papers which in his way of thinking actually led to or has actually quantified B, C, R properly or various aspects of it properly. And after examining those papers in some amount of detail, Bork comes to the conclusion that the focal studies strongly confirm the predictions of Hamilton's rule regarding conditions for social evolution and their causes. So, if the papas and the mamas in the field haven't figured out what it is it that we can do? Where does that leave us as of this moment? Of course, over time people will sort it out and over time this will come into the textbooks, but as of this moment, what do we do? So, what we are going to do is to take this advice from Joe Felsenstein, a very famous theoretical evolutionary geneticist. So, this is from his book Theoretical Evolutionary Genetics, where he says that there is no single canonical model of the evolution of social behavior. This one, which is Hamilton's rule, is useful primarily for its simplicity and nothing else. So, in other words, as of now, we should perhaps use Hamilton's rule more as a way of thinking, right. So, obviously for altruism to evolve, the benefit that the actor gets somewhere has to be greater than the cost, but this has to be balanced or this has to be weighted by the relatedness between the actor and the recipient. That is pretty much where we should leave it, and as of this moment we should not go for a very rigorous formulation, or rather we should remember that the Hamilton's rule, at least the way I showed you in this paper, in this discussion, is not a mathematically rigorous formulation the way let us say Hardy-Weinberg is, or let us say all those one locus models of viability selection that we were dealing with are. Okay. It is more of a thinking aid and nothing more. Now, obviously there are two ways of looking at it. One way of looking at it is this field, it is still not settled, but the way I prefer to look at it is that this is an excellent time to be an evolutionary biologist. A fundamental problem which we thought was resolved in the 1970s, 40 years later, now we know that it has not been resolved, people are still working on it, and this means that the field is alive, the field is active, and therefore again shows that it is a great time to be an evolutionary biologist. Now, till now we were dealing with the scenario where there was some kind of a relatedness between the actor and the recipient. However, in biology we have many situations where we find cooperation between unrelated individuals. So, obviously Hamilton's rule has that R in it, so that cannot explain any cooperation between unrelated individuals. Then what exactly can explain that? And one of the theories for that is what is known as reciprocal altruism proposed by Travers in 1971. So, what exactly does reciprocal altruism say? So, I will give you the formal statement in a minute, but prior to that let me just tell you, a way of thinking about it. So, here is a kind of a flow chart. So, suppose me and you, and suppose you do a favor to me, some kind of a favor, okay, and I notice the favor and I feel happy about it, okay, and because I have taken that favor, I either feel obliged towards you that I have to return the favor, or I really like you and I want you and I want to return the favor to you, okay. And this returning the favor to you is what is known as reciprocation, right, reciprocal altruism. Now, at some point later in future, I return you the favor, and now you have got a favor from me. Now, you start liking me, and then back and forth there is a positive reinforcement, and therefore, you are now likely to do me favors, assuming that you will end up getting a favor from me in the future. Okay. So, in some sense you are doing something good to me not because you are getting a benefit right now, but because you are expecting to get a benefit later on. Now, this can also happen in the other direction. So, suppose you have done me a favor, I have noticed the favor, I have felt happy about it, but I do not think that I am obliged to return the favor to you. I do not want to do you a favor, okay. And therefore, when time comes, I actually do not return the favor to you. There is no reciprocation, right. Now, when there is no reciprocation, what happens? You notice it, you remember that you have done a favor to me, but you are not getting a favor from me, and therefore, you note that, you log that as cheating. You did me a favor, I did not do a favor back to you. So, you do not like me, and therefore, in future you are unlikely to do any favor to me. In other words, if I do something to you and you do something to me, there is a positive feedback, and after some time I will do something to you simply because I expect to get something in the future. But somewhere if the chain gets broken, I do a favor but you do not return the favor, then I notice that, and after some point I say that okay, done, I am not going to do any more favor to you, right. So, this kind of a thing is what is known as reciprocal altruism, and formally it is a behavior where an individual sacrifices some of its own immediate fitness to benefit another based on the expectation that the other will repay the help later on. Okay. So, there has to be an expectation to get something in the future. Now, does this work? Do we have evidence to believe that there are some organisms which engage in this? So, turns out that there are a few examples. Now, in this particular case it is not very easy to empirically show reciprocal altruism either, but there are a few examples in the literature, and I will show you one such example. This is an example of an animal which looks a little scary, the vampire bats. So, vampire bats, they drink blood, that is their food, right. So, turns out that every single day the vampire bats need to go and forage, and if they do not find food, if they do not get blood, then they can tolerate starvation only up to 70 hours. After that they are going to die. Now, it is also true that not all forager is successful on all days. There are days on which a given bat will not get food. Interestingly, it is seen that the ones who have found the food, they actually regurgitate some of the blood and feed to those which have not got the food. Now, how do they know who has got the food, who has not got the food. It is thought that they just look at the belly, they see how much the belly is distended, and from that they can reasonably figure out. Now, since they can only stay without food for 70 hours, if you have got a good meal, giving it to somebody else is going to be a huge cost to you, although it will also be of a great benefit to the receiver. Now, the interesting bit is that it has been seen that all those individuals who end up helping somebody by giving them food, they are the ones who are more likely to be helped in the future when they do not have food themselves. And interestingly, individuals who have not helped others, they are the ones who other people or other bats refuse to help. So, this is a direct example of the tit for tat kind of a situation that is one of the ways in which reciprocal altruism can work. So, till this point we were looking at how relatedness can lead to altruism or cooperation, but there are situations where relatedness can actually lead to conflicts. It can be the root of certain kinds of conflicts, and those situations are what we are going to do in our next discussion. See you till then.